Welcome to the afternoon session. So Ewin Tang probably needs a little introduction. I think discovering her when she was an undergrad at UT remains one of the highlights of my career. She did her PhD with my former office mate, James Lee, at University of Washington. Is now a postdoc here at the Simons Institute. Has had breakthroughs on dequantization, also Hamiltonian simulation, and many other things, but is now going to continue the theme from Mark Jandry's talk about when do you need inverses and controls.
Okay, great, thanks. So this work is it's going to go the opposite way of a lot of Mark's points. I think Mark is not currently here, so I guess that's good. But yeah, so I'm going to talk about inverse and controlled unitary oracles. Just to recall like the broad setup, here I've listed my favorite quantum algorithms, Grover, Shor, Hamiltonian simulation, HHL. And we've developed these bunch of nice quantum algorithms, do a lot of really cool things. And over time, as we've discovered and analyzed these speedups, we've distilled them down into their sort of conceptual components. And when we do this, we find that often buried underneath, there's a unitary problem that's being solved. So, Grover's algorithm was originally had as input like a function oracle. But these days, it's more commonly used in the context of amplitude amplification. We express it in this way where we have a state preparation oracle, and it's a unitary that we receive as input, as opposed to just a specific kind of function oracle. Similarly, for Shor's algorithm, the input is a number, but the way we think about it now is as a phase estimation, where the input again is a unitary, and we want to find its eigenvalues or do something with its eigenvalues. And finally, the more linear algebraic tasks have been broadly unified under this framework of quantum singular value transformation. Your input is a block encoding, which is a unitary. And the goal is, this allows you to manipulate things and solve various problems by manipulating your unitary. And so overall, this motivates us to study sort of unitary problems broadly construed, where your input is a black box access to a quantum operation, which I'm going to call U. And the output is something about my operation, something about U. So for example, in the case of amplitude amplification, this output might be a quantum state, like a post-selected quantum state given my input. For phase estimation, or it might be like a classical output, like this particular property testing task that you can solve using phase estimation. Or finally, QSVT, your output is actually your input is a quantum operation, your output is a quantum operation also. And so there's been a lot of work sort of on the maybe more complexity side of trying to understand what's different when we go to this world of unitary problems. There's been a lot of interest as recently as 2 hours ago in this room, where Mark Jandry gave a talk about how you could model unitary oracles. And the question you run into immediately is, what does it mean to have access to a black box unitary U? Because typically these algorithms actually require more than just access to U. And we don't have the greatest understanding of why you need these. So these amplitude amplification and QSVT algorithms, they both require U and U inverse, so the inverse, what I'm going to call an inverse query. And phase estimation and things that use phase estimation typically require a controlled unitary, which is your unitary but with a control qubit to activate it. So if you want to have a theory of unitary problems that adequately captures all of these nice quantum algorithms, we need to understand what's going on here with all of these oracles. And so the central question of this talk is going to be the opposite of, I guess, Mark's talk earlier today, which is what is possible if you are only working in sort of weaker oracle settings. And so the first part of the talk is going to be talking about inverses. So what kinds of algorithms require both the ability to apply U and its inverse, and sort of why this occurs. The second part of the talk, sort of like I guess a bonus result, that I'm tacking on, which is about controls, and it's asking which algorithms require a controlled unitary and why. This is something for you to chew on as we go through the talk. And the central point is that we can actually get a surprising amount of insight on these questions with surprisingly little pain. The techniques will be pretty simple. And it sort of changed the way that I think about quantum algorithms in some senses. So I think hopefully it should be useful for you all as well. OK, so I think it's a interesting question in and of itself to understand what kinds of oracles you need for different quantum algorithms. This is in some sense like why do you need this assumption is one of the most standard things you can ask about some statement. But there are practical reasons why you might not have these accesses, or why you might care about this. So in the standard setting, the reason why you assume that you can have these stronger forms of access is that you're assuming that U is your unitary U is implemented on some scalable quantum computer. And when you do this, you get a circuit that implements the unitary U. And when you do this, you can actually convert that circuit. You can perform a transformation on that circuit to convert it to a circuit for both U inverse and the controlled U. So here, basically what I'm showing is that you can take some circuit and invert it gate by gate to get a circuit for the inverse. And so if I assume that one thing is efficient, then sort of they're all efficient. But stronger access is not always available. So I've recently been working a good amount on quantum learning. And in that field and the related domains of quantum metrology and quantum sensing, typically your unitary U is some actual physical system, or is implemented by a physical system. So you have some device, it's doing some quantum thing. And the quantum thing is a unitary matrix, which you're calling U. And so in this domain, you would expect that you can apply U, because that's what your system is doing. But being able to implement the U inverse is somehow somewhat harder. It's more or less the same as reversing time, doing like a time reversal on the device that's in your lab. And similarly, implementing the controlled version of U might require like taking your control line to the device and like quantizing it in some sense. Perhaps an extreme example is one of the cases where people use quantum enhanced sensing is this LIGO collaboration for detecting gravitational waves. Here, your unitary U is in some sense like a gravitational wave coming from somewhere in the universe. And so really they're able to get some quantum speed up in the setting, some kind of like some quadratic like speed up with an appropriate algorithm that uses applications of U. But in this setting, you could not do U inverse. It would be like, I don't know, reversing the universe or something. Or at least I wouldn't know how to do it.
So then how do they do it?
Their setting is a setting where you actually can get a quadratic speed up without using the inverse. So there are some settings in which you actually just do get like the quadratic speed up without using U and U inverse. I'm getting to this later.
All right.
Yeah. But yeah, great question. OK, so right, so this leads us into our first section, which is about inverse unitaries. So I'll just get it out of the way and answer the question of the title of the section title right now, which is that inverse unitaries can help. And an example was known, I think as the earliest example I know is like this 2018 paper of Pfefferman and Kimmel, where they show that if you give me as my unitary a permutation matrix, so it just swaps around the basis elements, then I could ask the question of, can I invert this? So if you give me, so then I could ask, like, what is the basis element that maps to, let's say, 0? Then, of course, I could solve this task with one query to U inverse, because I could just query U inverse on, or I could just apply U inverse to 0 and output that. But it's known using some variation of the adversary method that you require square root of D queries to solve it if I only have access to U without U inverse. But in some sense, I feel like this is like maybe not the most interesting example of a separation, just because this is a separation that you could witness in the classical world as well. Like black box inversion of a function is also hard. But this doesn't really capture the way that U inverse is being used in quantum algorithms that we see around.
I mean, the interesting part there, I think, is to get square root of d as a matching upper bound.
Yeah, that's correct. Yeah, the fact that square root of d is actually the right answer is interesting. Yeah, yeah, for sure. This is work, I think, this year.
Yeah.
Yeah. Okay. Yeah. So we consider the problem of amplitude amplification and amplitude estimation. So the basic setup of this task is that you have a unitary U as your input, and this is a state preparation unitary for a state that looks kind of like this. So here I have some good state and I have some bad state, and I have a flag which detects if the state is good or bad. And here I'm normalizing it so that these phi states are norm 1, and my amplitude A is between 0 and 1. And so with this, my amplification task is to output this state phi good, to output the good state. And the estimation task is to estimate the amount of mass that's on the good state. Okay. My formulation is to additive error.
Why is 1 an epsilon and 1 is 0.1?
Typically, amplitude, like the parameter in the amplification is going to be A. So I'm just going to do it in a way that there's only one parameter each. Like amplitude amplification outputs exactly phi good, right?
You said 2. What is this 2.1 error?
I'm just saying this so like the algorithm and the lower bounds are all robust to like output slightly. You can output something slightly different from phi good if you wanted to. Yeah. Yeah. These are not like. There's the definition of these tasks varies a little bit. This is like. This basically captures the entirety of the problem. Okay. So with this task, you can solve it in the following way. What I can do is I can just prepare a bunch of copies of U times ket 0, and then I measure my flag qubit and see if I get the good state. And if I get the good state, then I can just output it and I solve my amplification task. And for the estimation task, what I can do is I can just see how many times I see 0 and see how many times I see 1. That's a good estimator for A, or I guess A squared. And I can use that to back out an estimate of A. So if you look at what this naive algorithm performs, how it does, it requires 1 over A squared queries to U to solve the amplification task. And it requires 1 over epsilon squared queries to U to solve the estimation task. And this is like the naive thing. So the classic result of Broussard, Hoyer, Mosca, and Tapp is that you can actually do quadratically better if you give me access to the inverse as well. So for example, for estimation, 1 over epsilon queries to both U and U inverse suffice to solve the estimation task. To be more precise, like I think the original version required controlled U and U inverse. This version, as I stated here, is a result of Scott and Patrick. Okay. So so this is like the quadratic speedup that these algorithms get. And I want to say something that's a little bit stronger, which is that these algorithms are sort of the reason why quadratic speedups are so ubiquitous in quantum algorithms. If anything, like if you see a problem and ask for a quantum speedup, it would kind of be a surprise if amplitude amplification and estimation couldn't use it to speed it up in some way. And the reason for that is that these tasks speed up very fundamental primitives in algorithm design. Amplitude amplification speeds up brute force search, and estimation speeds up like counting. And so these are really like, in some sense, like they're like pillars of our broad quadratic speedup landscape. And amplitude estimation is going to be the focus of our talk. All of our results will extend to amplification, sort of as a corollary. Okay. So the question that we are going to ask is whether this quadratic speedup really needs the ability to query the inverse. So this is an open problem mentioned in a paper by Van Apeldoorn, Cornelissen, Gillian, and Nanacini. And yeah, they basically ask whether you can solve amplitude estimation in little o of 1 over epsilon squared time without access to the inverse. And then they also conjecture that the answer is negative. So it was around this time that I also became interested in this problem. And the reason I became interested was sort of a personal mystery. Around that time, Robin Zhang-Wan and Ryan and I got this result about unitary channel tomography. So it's also a unitary problem. The basic setup is that you give me access to some unitary channel. I want to output an estimate of this channel to epsilon error in diamond norm distance. And what we showed is that this can be done. The right complexity of this is d squared over epsilon. We have an upper bound and a matching lower bound. And the interesting thing is that this algorithm only requires forward queries to u. So it's able to get this 1 over epsilon scaling, this improvement over the naive algorithm d squared over epsilon squared, without getting access to u inverse. And so this is like, I thought already like a little bit kind of weird. But also you can use this algorithm, this channel tomography algorithm, to get improvements over the amplification and estimation settings when your dimension d is small. So in particular, like because this algorithm only uses forward queries, you can get this d squared over a and d squared over epsilon algorithm for amplitude amplification and estimation just by saying like I'm going to learn the entire unitary and then just see what the answer is. Okay. And so I was thinking like, okay, is this like actually is there actually two regimes here? Or is it just some artifact of like our lack of understanding? And if you dig into the literature in quantum learning a little bit more, you'll see that there are actually a decent number of examples where you can get this 1 over epsilon scaling without access to the inverse. So I've listed a few examples here. A notable one is this Hamiltonian learning from real-time evolutions result of Huang, Tong, Fang, and Su. And so these all get this quadratic speedup without inverse queries. And so the question is sort of what's happening here? What's the deal?
So is what they do in LIGO one of these?
Yes. Yeah. So it's this one. It's a spectrum. So if you want to learn an eigenvalue, learning an eigenvalue is actually like the 1 over epsilon scaling. Although I think to my knowledge, like the LIGO thing might actually just be something that they model it as being in like dimension 2. Yeah. And so in some sense, you never get this like separation in dimension 2. But yeah.
But you're saying it's a two-dimensional Hilbert space.
I think, yeah, I guess that's like, because they're
not in the regime where a Grover speedup would matter any, well.
They're in the speedup, yeah.
Maybe they could be because it's in terms of epsilon.
Yeah, yeah, they're in the speedup where it matters, or they do want the speedup, but there are ways to do it with forward queries that are like, yeah, that are generic, I guess, yeah. Okay. Yeah, because I think the idea is they're sending like a photon through, and so the photon is like a qubit or something. Okay. Great. So if you think about it a little bit, you might come to a feeling that like this actually, there's two regimes. Upper bound might actually be the right answer. And maybe like the general intuition for why there are two regimes is that if you want to estimate all of the features of U, then sort of what I can do is I can just cover all of Hilbert space and basically get all of the features, and I'm entirely coherent across the whole Hilbert space because I'm allowing myself to like sort of pay this entire this cost of estimating all the features. Whereas if I want to estimate just one feature, then I have to worry about like my feature sort of going off into Hilbert space and me losing it. And so this is why I get this like 1 over epsilon squared for a classical amount of noise there. So either I can cover all of Hilbert space to try to find the features that I care about, or I pay this classical noise fee. And the result that we show is that indeed there are two regimes. So we show that when d is very large compared to epsilon, then in fact 1 over epsilon squared is the right answer for in the forward query setting. And so there are indeed two regimes. There's like when D is small, it's like the quadratic improvement, and when D is large, there's a separation between U and U inverse. Okay, so in particular, what this means is that if I give you access only to forward queries, and if my dimension is large, then the naive algorithm that I mentioned before is optimal. And the naive algorithm is optimal in many senses. It uses, it can parallelize or it can do all of its measurements parallel or sequentially, or all of the circuits are like very low depth. There's no additional gates beyond just applying U. There's no entanglement needed, so it's really just like this is the right answer. Okay. So the task that we use to prove this lower bound is trace estimation. So the input is access to a diagonal unitary U. And so if you think about a diagonal unitary, the entries on the diagonal are going to be points on the complex unit circle. They're going to be phases. And what I'm going to do is I'm going to look at the average of all of the phases on the complex unit circle. And I'm going to see if it's close to the origin or far from the origin. So here, in this instance, all the entries of my unitary are sort of evenly spaced around the unit circle, and so their average is the origin. So I would answer true for this problem. Whereas like in this case, it's more skewed towards one direction. And so it's far from the origin, and I would output false. And so I'll leave it as an exercise to show that you can reduce this to amplitude estimation. It's just about the matter of defining the right circuit. But this shows that you can solve this task with 1 over epsilon forward and inverse queries. But without it, you get in this like two regime setting where you either need to learn the entire unitary, or you need to pay this classical noise. And I'm going to simplify this a little bit more into a task of distinguishing random unitary ensembles. So the thing that we prove a lower bound against is this task where I sample a bit at random, and then corresponding to that bit, I sample a unitary from that ensemble. So if I see 0, I sample a unitary from ensemble 0, and if I see 1, I sample a unitary from ensemble 1. And these are diagonal unitaries, and their entries are IID drawn from either the uniform distribution around the complex unit circle, or a distribution which is slightly biased towards having positive real part. So this diagram here is of the PDF of the distribution. And so if you note that like it's slightly weighted towards like +1, and so that means that if you look at the expectation is going to be like around 5 epsilon, which is far from our 2 epsilon criteria, or 2 epsilon cutoff. And our goal is to, given this unitary U, guess the ensemble it came from with good probability. And the point is that when you define this, this task reduces to trace estimation, and therefore amplitude estimation, when your dimension is sufficiently big. The reason you need the dimension to be sufficiently big is that if you think about what the normalized trace is doing, it's looking at the average of all of these points, and so you need it to concentrate to the mean. And so when D is sufficiently larger than 1 over epsilon squared, it'll concentrate to the mean, up to epsilon error. Okay. And so all that's left is to prove a lower bound against this distinguishing task. A lower bound of 1 over epsilon squared queries will suffice. Okay, so this is where I was in like 2023. I was thinking about this problem a lot and getting kind of stuck trying to think of like lower bound techniques. If you were talking to me in like the fall of 2023, you'll know that I was thinking about this a decent amount. And the issue with these lower bound techniques to try to prove this is that basically there's not that many techniques out there that can distinguish between a forward and an inverse query. A lot of the suite of standard techniques come from quantum query complexity. And so that means that these techniques sort of, at least in their native environment, they don't care about a forward and inverse query because for a function oracle, they're identical. There are generalizations of all of these things to just general oracles, non-function oracles. But things tend to get a bit hairy. So this is where I was stuck a couple years ago. And then I started talking to John about it. I was complaining about how, how I was stuck on this. And John asked, like, have you tried purification? I heard this purification thing is really good. And I was like, okay, maybe not implausible. And so we started trying it. So the compressed oracle method, or purification, is something that's seen a lot of excitement in recently as last month in this room. And the basic point is that the basic point of the compressed oracle method is that you can analyze random ensembles of states or unitaries through their purifications. And this can be a lot easier than the standard route of doing this, which is using representation theory. And so the basic idea is that, like, okay, you sort of, there are a lot of linear algebraic techniques that can handle these purifications, so you don't have to break out the heavy machinery. So I'm going to give like a high-level sketch of what's going on in the proof. I'm not going to get into the details because it's notationally heavy, and I don't want to introduce that stuff. But I will emphasize that the proof is like pretty simple. It just is a matter of rearranging things in the right way. So the fundamental, I guess, object in this proof is decomposing a quantum circuit into Feynman paths. So we can consider an algorithm that tries to distinguish between these two ensembles. And we can imagine it as being some quantum circuit which applies my unitary, let's say, n times. And then like measure some observable after that, and then outputs the resulting thing. And the goal is that you want to this circuit to distinguish between the two ensembles, right? And so you can write down this circuit. And you know this unitary is diagonal, so you can write it in this form as the sum of the diagonal entries. And I'm going to call this circuit, that circuit output, alg sub u. And this, I can use the distributive property to just expand out all of the u's in the circuit in terms of this sum. And what I get is that it's a sum of a bunch of these, like, what I'm going to call Feynman paths. And what these Feynman paths look like is it's sort of this, I replace every instance of u with these x1, x2, so on through xn. So this, so far, this is just, I just used linearity of like the circuit. And the point is that this Feynman path state, like the intuition you should have about it, is that this is the part of the output state which, as you went through the circuit, queried u on the indices x1, then x2, then x3, and so on. And then when you queried the u, it attached a phase of ux1 times ux2 dot 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 through uxn. And so when you consider now, looking at a unitary drawn from this ensemble, unbiased ensemble. So here, this is like ensemble 0. It's just like the entries are random phases. Then my output state looks like the expectation of my algorithm state over the u drawn from this ensemble. And it turns out that you can write this as the partial trace of a purification of this output state. And it'll look like the following form. So it'll be a sum of these Feynman paths. And attached to every Feynman path is the histogram of the path. So for example, like if my Feynman path was, if x1 through xn were all ones, then this would look like n 0, 0, 0, 0, 0. So it's like the number of times that any particular thing is queried along my path. OK, so what this means is that if I look at these histograms, if I look at a particular sequence of x's, there's a corresponding histogram. And all of the histograms, these are like an orthogonal basis. So essentially what happens is that when I perform this partial trace, I'm going to get either it's going to split into a bunch of orthogonal things. And so my partial trace is going to split into a mixture of superpositions of Feynman paths. Do I have like a slide that's more precise about this? Yeah. So to be even a bit more precise, what you see is that your output is a mixture of these expressions, where these expressions are superpositions over Feynman paths with the same histogram. Okay. So it's not super important to understand the details of this, but essentially, like the main point is that there's a very nice expression of this output in terms of the Feynman paths, and like your purification gives you this. Now, if you look at what the biased ensemble is, so this is already like you're pretty heavily using like your purification method here. And when you draw from the biased ensemble, you need to do some more fancy things. Like there's a Fourier transform in the original thing that you replace with a biased Fourier transform in the new thing. And now when you look at my algorithm running on the biased ensemble, the thing that you're going to get is the partial trace of a bias purification, where I can express my bias as being some bias that's entirely contained in the purification. Right? So there's still this Feynman path component, which is identical between the two. But there's also this error thing that's happening here, this deviation from unbiased to biased. And the important structural lemma, is that these errors are actually orthogonal to the histograms. Like it's orthogonal to the main component, the sort of unbiased component of my output state. Now, the reason why this is helpful is that actually these kinds of errors are very nice. So let me consider a sample, like an example purification. So consider this state psi, where it's an unnormalized state, but it's basically the identity, but I purified it. Okay. And now I consider perturbing this state only in the purification. Right? So I'm perturbing this state only in this purification register. So I've added this element bot. And the important thing is that bot is orthogonal to both 0 and 1 in the purification. And then when I trace out my purification register, the state that I get is this state, which is actually epsilon squared trace distance from the original state. And so the important thing here is that you are changing your purification by like order epsilon. But in fact, because it's orthogonal, it's an incoherent error. It's an error in the probabilities of the mixture. And so this means that the difference between the states after I trace it out squares. It gets smaller. If I changed my state to be perturbing it within the space of the purification, so now I'm perturbing it in like the 1 direction and the 0 direction, which is where the purification already lives. Then when I trace it out, I actually get a state that is only order epsilon far from my original state. So this is like sort of where I'm getting this improvement from 1 over epsilon to 1 over epsilon squared. So that's the basic idea behind the proof. Yeah?
I got confused. Which kind of errors are happening in this case?
This kind of errors are happening.
But
So
in the previous slide you wrote like an error sub h, so like now you're having it not depend on h?
Oh, in both cases the error, okay, so what's relevant is like this could be a bot 0 and this could be a bot 1.
Oh, all that matters is that it's outside the span of 0 and 1.
Yes, yeah.
And just for intuition, on the previous slide, like, should I think of these error h's as like what happens if you purify something where like the phases come from like the right half of the unit circle?
It is not quite that simple. So like, essentially like there's something actually going on within the purification layer, because if you look at the two distributions, the one where I sample D things from the biased thing versus D things from the unbiased thing, these things are very far in trace distance. So you're really like, so So you're really doing something to like get this sort of epsilon different thing to be looking close to your original distribution. Yeah. Okay. Yeah, good question. Okay. Any other questions? Okay. Right. So if you weren't following what I said, the basic point is that when I run my algorithm on the unbiased ensemble, it produces a mixture over these Feynman paths. And when I run it on the bias sample, there's some deviation. And if I don't have access to U inverse, the deviation is going to be only in the probabilities of this mixture. But if I do have U inverse, then the bias can be in the components of the mixture. So it's like the difference between like an incoherent error versus like a coherent error. And that's why you get this separation between the two. That's why you can get this 1 over epsilon squared lower bound. Okay. So that's all for the first part. I should, again, stop for questions in case there are. Yeah.
Does your lower bound meet the min of two things upper bound that you presented?
No. So we get like a, yeah. So this is, so we're loose on the first part. We're tight on the second part. So if we're D sufficiently large, we're tight, but we don't know what's happening in the intermediate regions, where D and epsilon are like polynomially close.
Do you have a guess for what the right answer is? Is it just the upper bound, or?
My guess would be the upper bound. We didn't really try to tighten the lower bound. Yeah. It would also not be crazy for me, like to me, if the upper bound was not the right answer. But yeah. Other questions?
In this problem, like when you're only talking about diagonal unitaries, just like learning, presumably learning it is easier too, right?
Yeah, you can't get the d squared. You can't get a d squared with R instance.
Is this understanding tight for diagonal unitaries maybe?
I don't think it's tight for diagonal unitaries. Diagonal unitaries would be d over epsilon, whereas we just get d in the first part.
Okay.
Yeah. Okay. So now for our second part of the talk about controlled unitaries. So actually this came about because we were wondering if our lower bounds also held against controlled unitaries. And so again, I'll answer the question on the first slide. So we know that controlled unitaries do sometimes help, in particular to distinguish the global phase. So the definition of the controlled unitaries here, it's like a block of identity plus a block of U. And what happens when you look at a controlled unitary is that the global phase of U becomes a relative phase in controlled U relative to the identity part of it. So things that wouldn't be detectable using quantum computers could then be made detectable if you went to this controlled unitary. So for example, like very simple instance would be, I imagine I have access to this like phase oracle for a function. This function is taking 0, 1 to 0, 1. And I want to understand what is f of 0. Well, if I don't have access to this unitary, then I can't distinguish the unitary being identity from negative identity. So I can't distinguish between f of 0 being 0 or being 1. So I can't do it without controlled unitaries. But I can do it with one query to, or I can't do it, I can't do it without controlled unitaries. If I do have it, I can just do it in one query. But in some sense, like in defining my talk and giving the definitions, I've done a little bit of sleight of hand, where when I talked about unitary problems, I said that the input was this ability to apply the unitary U. And what do I mean by that? Well, I mean when I say apply U, I really mean I want to apply the channel which maps the density matrix rho to U rho U dagger. Right? And so this phi U doesn't care about the global phase of U, because as we know, so phi U and phi of a phase times U is identical. And the output is something about, I said it was like something about U. But what I could mean is either the output is something about the unitary U, like the literal unitary matrix U, or my output could be something about the quantum channel corresponding to U. So like I could be asking about something about the quantum channel phi U. Now, in some sense, this is like questions that are like physicsy all take this kind of form, right? You get access to a channel, you want to understand some property of the channel, you want to do tomography, you want to estimate observables, et cetera, et cetera. Physical properties of the channel are more of this flavor. Whereas like sometimes you might end up defining problems, if you're like coming from a computer science perspective, you might end up defining problems which are really properties of the unitary U, right? And sort of rely on this global phase. And sort of here, if you think about when is a controlled unitary something that makes sense, well, when my output is something that is, when my problem is something that depends on the unitary itself, then it makes sense to consider the global phase. Like if I ask you to give me the controlled unitary, this makes sense as the thing to give me. There's like a correct choice. Whereas if my output is something about the quantum channel, then really what I've done is I've stated the entire problem without any reference to a global phase, right? And so it doesn't really make sense for there to be a canonical choice of a controlled unitary. So all controlled var phi times u, all phases of u are equally sensible as choices to pick for my controlled unitary. And so the result I want to state is that, okay, as we know from the example I just gave, in the first setting, we know the controlled unitary can help. In the second setting, we can show that the controlled unitary cannot help. And what we mean precisely is that if you have some circuit which uses a controlled unitary and also, maybe it's inverse some number of times, n number of times, then I can convert that circuit to a circuit which uses only the unitary u. And the output of the circuit is going to be a mixed state. In particular, it's going to be the circuit applied for the controlled version of a phi times u for a uniformly random phase phi. So basically what it's doing is it's saying like, if you don't care about the phase, I'm going to output you the solution where I use a random one instead. And this circuit is nice because it doesn't use the controlled versions any longer. It replaces every controlled version, every controlled query, and its inverse with the corresponding uncontrolled version.
Does C prime also need U inverse?
C prime also needs U inverse. So it replaces CU with U and CU inverse with U inverse.
Okay, so it's saying that phase is the only obstruction.
Yeah, yeah. It also works if you like with transpose and conjugate. So.
So if the original circuit only had forward queries, the new circuit would still only have forward queries?
That's correct. Yeah.
Okay, if you had access to U and U conjugate, for example, or U and U transpose, then that would be good enough.
Sorry, what do you mean?
Sorry. Okay. So what's the statement about transpose? Like, if C used CU and CU transpose, then C prime could use U and U transpose.
Yeah, that's right.
And so forth.
And so forth, yeah.
But like it doesn't matter. It's just like whatever unitaries you have, right? You're just removing the controls from each one like separately. But
yeah, that's right.
Oh, so okay. So also, if C only used CU, then C prime could only use U.
Yeah.
Okay. So you don't actually, the inverse and the conjugate stuff is not even relevant to this.
Yeah, I suppose. Yeah.
Okay. All right. Got it.
Yeah. Yeah. I would have to think about it for a second. But
Okay.
yeah.
Okay.
Yeah. Was there another question?
I had the same question.
Oh, okay. Cool. Right. So the point is that if my circuit C solves a problem and my problem is a problem on the quantum channel, it's like phase invariant, global phase invariant, then the C prime also solves the problem. So let me give an example. So suppose that we have an algorithm which can estimate U applied to 0, so the density matrix of U ket 0, if I get access to controlled U and controlled U inverse. Right, so this is like your standard state tomography type question. except now I have a state preparation oracle, state preparation unitary. Then when I decontrol my circuit, I get some circuit which outputs a random output of my circuit where instead of u, I use phi u. And this thing is going to be an estimate of, well, it's going to be an estimate of that state, but with u replaced with phi u. But we know that the global phase doesn't matter, so this is the same as the original thing. And so the output of my circuit is going to be the output I want from C originally. And so in general, like for general kinds of problems involving state preparation unitaries, it shows that getting controlled access is just not helpful. So for any like physical property of a state, getting access to the state preparation unitary is not helpful. Another example is PRUs. So we can show that if you have some random unitary ensemble, which is pseudo-random under access to U and U inverse. So what this means is that I have some, like, I can't distinguish a unitary drawn from my ensemble versus a unitary drawn from Har when I'm allowed to access U with these like polynomial gate quantum circuits. If I have such a pseudo-random unitary ensemble, then I can construct an ensemble that's pseudo-random also under controlled access to U and U inverse, just by taking my unitary U and attaching a uniformly random phase to it. Okay, and you know, if you're this phi, it doesn't have to be uniformly random. It can instead be like a poly n to the root of unity if you're worried about implementation details. And so this gives an instance of these like sort of PRUs that is like stronger than like the strong PRUs that of Ma and Huang, which work under U and U inverse. I think this was sort of morally believed that you could do this, but this gives a very simple generic way to actually perform this, to actually prove this thing. Okay. So,
Sorry, is there a PRU that's insecure with control query, but secure otherwise?
Not to my knowledge.
There's ensembles that can be distinguished with like exponentially many queries that, like, if you like, I don't know, consider like, yeah, attacks that like learn the determinant or something. If your determinant is like not uniform or something. So this would like thwart that, I guess.
Hey, not to speak for Fermi, but Fermi has also told me that he's like 99% sure, like the Ma and Huang proof, it just goes through with controls.
Yes.
But it's just too much of a notational pain to add, you know, controls everywhere in the paper.
Yes.
But this allows you to get the result without having to do that.
Great. Yeah, I agree with all of this. Okay. Actually, it's the literature on this topic is a bit interesting. Like I think if like I think this result is like actually, you know, not that hard. It's like sort of I'm going to mention it's like morally like a kind of folklore. But when we ask people, okay, do you think this thing is true or false? They were kind of surprised that you could actually do this thing where you replace controls generically with uncontrolled versions. And I think you know, part of the reason is that there's a lot of this like negative prior work, which basically says like you can't implement controls, don't even bother trying. And these are working in the setting where you have a unitary and you want to implement a particular controlled unitary. So for example, you want to implement the controlled unitary whose determinant is 1 or something. And so there you genuinely do have all of these weird like topological type of obstructions to implementing the controlled unitaries. If you just care about implementing a random one over the course of a circuit, then it turns out you can actually just do this. And we are not the first people to observe this. So there's this paper by Sheridan, Maslov, and Mosca which solved one of Scott's like 10 annoying problems. Yeah. So hidden in the appendix, there's this a similar, slightly weaker result in controlled unitaries. It can get the state preparation statement, but it can't get the stronger PRU statement. That's just like sort of where it sits in the hierarchy. But in any case, like part of this talk is just an advertisement that like you actually can just generically get rid of controls, and this is the reason why. Okay. So I'm going to give a brief explanation of why the statement is true. Right. Okay. So let me write down quickly the basic setup. So the basic principle behind why you can remove this is fairly straightforward. So I can imagine that I have some circuit which uses a controlled unitary n times. And the goal is I want to simulate my expectation over a random phase phi of my circuit applied to controlled of phi u. Okay, technically this is like a mixed state that I'm writing here. And when I consider like n equals 1 query, query algorithm, this should be hopefully illuminating for why this is true. So for a 1 query algorithm, it looks like the following. So I'm applying a controlled phi u times some unitary a times ket 0. And this is the thing that I want to simulate for like a random phi. And what I can do is I can take this and I can write this control using this fact of like controlled phi u is equal to 0 tensor identity plus 1 tensor phi u. So I can just plug in this fact into my quantum state. And I get this part, which is the part where the control bit is 0, plus phi times the part where the control bit is 1. Okay, so what does this mean? Well, now I can take this circuit, okay, I'm gonna give notation to these two parts. I'm gonna say this is fp0 plus phi fp1. This part I'm calling fp0 because it's the part that queries the control bit at 0, and this is the part that queries the control bit at 1. And so here I can write my expectation. I can write this thing as the expectation of fp0 plus phi fp1 times the conjugate transpose and I can expand this out. So I'm going to get a term that looks like fp0, fp0. I'm going to get a term that's phi fp1, fp0. I'm going to get another term, fp0, fp1. And then I get a final term that's fp1, fp1. Okay. And the thing to notice is that when I'm averaging over a uniformly random phi, the cross terms cancel. And phi times phi star is equal to 1. And so I get that this is just a superposition, or sorry, a mixture over the fp0 and fp1. So it's a mixture over the two Feynman paths. And so you might see that one way you could simulate this One way I can simulate this is by saying I can take my 0, my control bit, and my other register. I could apply A, and then I can measure. And then now my bit is classical, and I can control on this classical bit to apply my unitary U. And this actually gives me the same mixture over the Feynman paths as this. If I wanted to not use a classical control, another thing I could do is I could say, well, I'm going to add 2 different registers. And what I'm going to do is I'm going to, well, first apply my A. And then for my control bit, if my control bit is 0, I want to apply U to this register. If my control bit is 1, I want to apply U to this register. So the way I would do this is with a controlled swap. 2 controlled swaps. And a unitary here, my unitary here. And so here I've gotten rid of my controlled unitary, and now it's just a U. And finally, what I'm going to do is I'm going to do a controlled increment operator here. And when you look at what the output of this circuit is, if my control bit is 0 after this point, then what I've done is I've applied U to 0 and I've incremented this register. So I get, so my output state has this part. And then here, this is U0 tensor 0. Or I haven't incremented the register, yeah. And I also get a term for if my control register is procced. And then I apply U to this register instead of this one. And then I increment this. So this is 1 tensor U because I'm applying U to this register, A0. And then here, this is 0 tensor 1. And you can see that when I trace, this is my purification part. And when I trace this out, these 2 parts are orthogonal. And so what I'm getting is a mixture over these 2 quantum states.
It's 3 o'clock. We should
Oh, yeah, sure.
wrap up soon.
Yeah. Anyways, this is how you do it. And if I want to do more generally, I can just iterate this gadget. Just apply it. Well, just replace every controlled unitary with this gadget, and it works. OK, so yeah.
Does this still work if, like because for each controlled U, you are applying the same global phase?
It's all right.
For each controlled U, you're applying the same global phase?
Yeah, like you're applying the same global phase, not an independently random global phase.
I'm writing down the. Actually, can we talk about it after?
Okay.
Yeah. Yeah, I can. It's over a uniformly random global phase. So I wrote down the expectation over the phase, and now I'm showing how to simulate that expectation. Okay. Yeah. Okay. Just to. Yeah.
Is the number of ancillas you use scale with the number of times the control unitaries appears in the circuit? Yes.
There is a. I mean, yeah. If you don't want that to happen, there's the way. The previous, the Sheridan, Maslov, and Mosca thing does do that without an ancilla that scales with the number of times you apply it.
It scales like log in the number of times you apply that, right?
Yes.
It's counting, so.
Yeah.
Okay.
OK. Cool. Just to recap, what we showed is that we have amplitude amplification and estimation, which require. We showed that it requires both access to the forward and inverse queries. And the interesting thing is that we were able to get this, show this for a problem where the reason why you use the U inverse is morely like about coherence. It's like sort of on computation kind of flavored. And secondly, we showed this result about controls, which is that controlled unitaries can help for global phase, but in some sense, this is the only case where it can help. And so I found both of these results pretty surprising. So what I expect is that you could get a lot more insight just by thinking about more questions related to these topics. Okay, thanks.
Okay, maybe some quick questions for Ewin?
What's the query and maybe like ancilla overhead of the control result? Like, do you need any extra ancillas when you translate the controls?
Yeah, my knowledge, okay, so my current understanding is that the number of ancilla you need log n ancilla, and you also need an additional ancilla, like a log d size ancilla to like another thing of the size of the unitary. You can get rid of the counter if you want, but that gives a non-uniform distribution over the phase. Furthermore, like there's also settings in which you can like reduce the log n to like a q size if you know that u to the q is the identity. So there's regimes in which you can get like a more limited statement, but there, as far as I know, there's no way to do it with like 0 ancilla. Yeah. And also the gate complexity is similar. Yeah.
So you gave a list of problems where you can get 1 over epsilon scaling with only forward access. Mm-hmm. Do we like have an understanding of like what features these problems have that let you get this type of speed up?
I think they're all of this form where like if you like I don't have a great answer. I think it's just like you want some kind of like algebraic kind of structure. So if I want to learn in some class, then maybe I only need to, the number of queries that I need, the number of forward queries I need might only be the number of parameters of the class over epsilon or something. If the class is sufficiently nice. That's sort of like what the regime in which all of these get these kinds of results. For like Hamiltonian learning, sort of what's morally happening is that like if I only perform short time evolutions, then I'm not like going off into Hilbert space. I'm like sort of remaining fairly localized, and so I only pay the Hilbert space dimension of like the local region or something. But yeah, so it all kind of makes sense if you like consider this as like, okay, I'm trying to like learn a class, and like what like I can get 1 over epsilon if I want to learn the class. But if I want to estimate one feature of the class, then maybe I do 1 over epsilon squared.
Okay, maybe a last question. Yeah.
Maybe like I'm wondering how your results compare to like another paper. Like there's some paper by I think Yoshida and some others, where they show that if you have like access to a unitary, you can, and let's say it's d by d, you can call it like possibly an exponential number of time or something, but like implement exactly like the inverse.
Yeah.
So I suppose that if you have any algorithm which does like a 1 over epsilon scaling on something, where you call like a unitary, you can always somehow get rid of using the inverse, but at the expense of possibly like a large overhead in the dimension.
Yeah, yeah.
So I guess I'm wondering, like, have you looked at this, and like, is this much better than what they are doing? Like, do you gain a lot of it?
Oh yeah, I didn't mention this, although probably I should have. There are like sort of ways to convert forward queries into inverse queries, forward queries into conjugate queries, etc. I think these get actually slightly worse than the thing for the amplitude estimation. The reason I didn't do it is because actually you get slightly better just by learning the unitary directly and not converting the queries. It's like d squared versus d cubed or something. Right. But yeah, it is a case where you can sort of generically convert circuits which use the inverses to circuits which use only forward queries. And you only lose like d cubed and like polylog in the number of queries or something. Yeah.
Okay, let's thank Ewin again. Now break, and the next talk's at 3:30.
Thanks.
Yeah.